Right. Next up, we have Dr. Guillem Bernat. Guillem is CEO and founder of Rapita Systems. His background is he's a PhD in computer science and did a postdoc in the real-time systems group at the University of York. He's a lecturer there before leaving to run Rapita Systems. He's an honorary visiting professor, I think, at the University of York. He's going to talk to us about how to get 100% code coverage.
Good afternoon, everyone. I should start with a disclaimer. In this type of events, of course, my interest is to sell my tools and show how great they are. But I don't want this to be a sales pitch because you haven't come here for a sales pitch. At the same time, we want to do this to be a wider context. And the things that I don't like is when I go to a conference and somebody's making a sales pitch underneath of something with no substance. So I promise I'll do my best that you come out of this meeting with something that you didn't know. And if you didn't know that because you are already thought about this, so therefore, you are at the right place. But of course, I have to disclaimer to say that in the end, what I want is to have people come to me and say, "Oh, that was good. Can we do this? Really? Let's talk together." Okay? So it's a balance between an academic conference and a company presentation. Okay? So that's a start. So the focus of today is on how do you do code coverage as a measure of part of your testing process. And the problem is code coverage is a metric to see how well your tests are. And if you have a strong requirement to achieve 100% code coverage, people know that this is quite difficult. And we've done a lot of effort to put our tools and our expertise into making the process of claiming 100% to be as efficient as possible. So can I ask maybe a question here? So how many of these people in the audience have to do or know what MCDC is? You have not heard it at all. Okay? So this is important because I need to get the pitch right, so everybody gets either bored or this. So MCDC is a metric of coverage of source code that says that you have to almost try all the combinations on a big decision. So you have if A and B or C, you really need to make sure that you toggle A and you toggle B and toggle C, and then these have an impact. And time it takes to achieve 100% MCDC coverage. Okay, I don't know. With my customers tell me that sometimes people spend months, if not years, of testing to generate that 100%, which is tricky. So the context that I'm doing today is to talk about safety-critical systems. Okay, and there's been a bit of a discussion here of why are we doing testing. So the focus of we are on the absolute extreme. I remember a very nice sentence that somebody says, there are two ways of building systems. Systems that work and systems that don't fail. And the difference is about between 1 and 2 orders of magnitude on the dollar sign or pound sign of the cost of making them. And I see something people nodding, which means that we are the right audience, and some people, this doesn't any meaning at all because you haven't suffered that. But for me, I get very comfortable to jump on a plane because I know how people that make systems for aircraft, how meticulous and how deep they analyze it. In a new car, maybe. Medical devices, even less. So there is a culture shift. So I apologize if somebody in the audience are more the general IT, and the things I'm saying here look a bit too much. Now we're going to ask the question. So what is the cost per line of code? So if you make a big project, choose a project, people over here, how much is the expected line cost and pounds per line of code? Anyone? In your experience? You know, because you are safety critical. I know you'll have the answer. How many lines of code an engineer does a day? A couple of hundreds? Yeah? That's a safety critical one. Yeah? So, you know, because I didn't going to calculate it. Some estimations there's about anything between 10 and 20 to about 40 pounds per line of code. The shuttle was 1,000 pounds per line of code. That's where the two orders of magnitude comes in. So these talk here, we end up, we spend hundreds pounds per line of code, which is maybe, tens per day. Okay, no more than that. And to the point of these agile methods that we asked before, well, some engineer says, well, I know this line is wrong, but I cannot touch it, even to change the semicolon. Yeah? Because changing that number means about a week's work. Getting reviewed, getting retested, getting documented, certification, rerunning the tests that take weeks ahead. So this is the context that put it in. So we are making safety critical systems. It is absolutely required because the culture and the standards, well, standards, the one say NAB, the guidance says that. So, same comment, but in more like an infographic. So what is co-coverage? I think the other thing that drives a nagging concern. I have a few comments here, and some people say, well, we don't have 100% code coverage because MCDC or statement coverage is very difficult, so we have a tool that automatically generates the test cases for me. And therefore, I get 100% code coverage. That's an elephant in the room quoting. Why is that? I've been asked by customers, says, do you have a tool that generates code coverage? Yes. Exactly. And the tool is source code because we've got that text. Yeah. So there are tools out there that do that, and I'm really hesitating to have to say, I do not want to do that because I don't want to claim that, well, you wrote your code wrong. This greater than should have been smaller than. The tests automatically generated is 100%, but you didn't check. So the context here is this part of the V, is that you have requirements-based testing. Independent teams, one develop the requirements and design and development. And the second testing team is look at the requirements and independently develop the tests. And without looking at the source code, let's see where we can achieve 100% code coverage. And that's where it becomes tricky. So that's really what we want. So we have a tool called Rapita, specialized in doing on-target code coverage, so that you have evidence as close to the final system, so the end target, the end processor, end object code, as close to the final, that you achieve 100% MCDC. That goes again to the complementary talk we heard before about MATLAB link, that yes, there's been some talks about that you can do testing on the host, and then if you run this on the target, that's okay. But that's okay if you can make the mapping that while you're testing on the host, it actually has the same behavior as on the target. And we've seen more and more certification authorities insisting that, well, you want to do it this way, then you have to do all this to work to prove to me that this evidence is correct. However, if you do the testing on the target, that's different. And of course, the plus permanent target is that there are very little resources left. So that is really the conundrum. And that's where we put our efforts. So what the unique thing we do is that we make sure that we can do code coverage on target with a couple of assembly instructions per instrumentation point. Maybe 2, 3, 4, sometimes 1. Okay? So, I have 100% code coverage, therefore, my code is correct. Big fallacy. So one of the first things to know is 100% code coverage. It just means that you tested all your exercise lines of code. The testing shows the presence of bugs, not the absence. Okay, that's something that I've seen in some industries, and I'm going to say which, where people derive testing of achieving code coverage as an objective per se. When you achieve 100%, then we are okay. And you do that whatever means and at whatever cost. Not realizing that what you should be doing is you test to make sure that the code is correct. Your code coverage doesn't mean that your sub-requirements are correct. And there's the typical picture. Really, you know that where from what you told, the customer told you, when the developers did, whether it was documented, etc., to what, in the end, the customer really needed, is different. However, what code coverage does is to show you that at least it's thought independently of code coverage and requirements. Tricky example here. Compilers are very robust and very good. Except very points, somebody people know why this example is wrong. Come on, you know that.
The rules, such as they are, say that the operating systems revolve on variable source code.
Correct. So we have a compiler, you see, that you want the frequencies of C with what that constant volatile means. Constant you can only say once. Volatile means that these things can change any time. However, the compiler got it wrong, and the piece of code in the middle here, piece of code in the middle here, where you just don't read the variable and put it into another variable, and you don't do anything with it, the compiler says, I can put it outside. Because that was a const variable, the comparing layer was volatile. This could be reading from the register, and reading from that register means that that device is alive. If you don't read from the register, maybe that device dies. So that's a compiler book. We can achieve 100% code coverage on this, but the error is still there because the compiler has issues. Another one is, another one of the tricky questions of avionics is, what the ON7AB tells you is that you have to have 100% object code coverage. But finding what the object code is very difficult. So the argument is either you design at the object code level, tricky one, or you do at the source code level, and then you have to prove there is a one-to-one mapping between source code and object code. And if you don't do that second step, it could be that the compilers added things that you didn't know. And some compilers are good at doing some of these things, but some of compiler optimizations mess up the code tremendously. And the last thing you want is to have spent a few of your years of productive life looking at disassembled object code. I tell you, this is not a very nice and enjoyable thing to do. But sometimes somebody has to do it. Second, another point to make here. This is, what is code coverage? Well, it depends a lot on what industry are doing on the level of criticality. So the easiest one to do is what's called function coverage. Have I called every function at least once? Statement coverage. Have you executed every statement at least once? These are required with a lowest level of criticality. Between avionics, which is the ON7ABC, and automotive, they are basically equivalent. At the higher level of criticality, you have to go to both decision coverage or branch coverage, is a big distinction of that, and all the way to MCDC. And MCDC is where the big pain comes in. Automotive industry being very clever here is that they only ask you to do MCDC at the unit test level because they know that it's so difficult to do it on the target that there's no effectively resources. The 8-bit microcontrollers with 32 bytes left of RAM, very difficult to do anything else than just basically function boundary instrumentation. So in the context you can read the discussion that we'll do later, that if you have low criticality systems, we are just basically checking that every function is executed. We have high level of criticality, is almost checking all the combinations in a decision have been executed. So, one point to do here is, and I have to admit that I haven't been done testing and achieving 100% coverage on a safety critical project. But I've been very fortunate to talk to a whole range of people all over the world where they come and cry on my shoulder and says, you don't know, you cannot believe the amount of time we spend doing X, Y, and Z. So, without knowing anything, I have been able to collect information over the years to say that their headaches are usually classified on missing requirements, missing code coverage, missing tests, dead code that shouldn't be there, or deactivated code, to explain that in a moment what it is, and then some things which are a bit awful, which is compile errors, for example. Now, if after the end of this talk somebody wants to say other classes of defects, please come back to me because I want to extend that list later on. Number one is I run all my tests run it on my system, and there are still some piece of code that hasn't been executed. If you're delivering your tests, it means that there is some code over there that has been tested, but is not attached to a requirement. Right? Because if you do requirements testing, somebody is implementing something, but the tester doesn't know that's implemented because that requirement is not there. So one of the reasons you can do it, your requirements are wrong or incomplete. And therefore you need to go back and refine requirements and start all the design process again. So under requirements, and then from the requirements, whole review process, give it a new tests, and then run the test again, and go back to square one. The second one is the requirements are right, but because you haven't explored all the combinations of the tests, it means that you haven't been able to test all the combinations, or you missed a particular mode. So the other option is that what is wrong is actually the test environment. Okay? And that is the usual interpretation that what has to happen. So you have to make the tests, and as part of the test, go back to square one, because then you may be able to find other things. Dead code. So what is dead code? Dead code is simply that in the Guillem 7AB says it shall not be in the final code. So if your tests are correct, and you have all the requirements, and you have still bits of code that you cannot achieve in the code, is code that you cannot execute. If that code you cannot execute it shouldn't be there. Because if you haven't tested, you don't know whether it has an improper behavior, and that can jeopardize the aircraft, etc. So this is a typical one where, on purpose you wouldn't do that, but if you put in a mode that says if mode isn't stationary, do something, that piece of code there is dead, because that can never happen. Now, this is the obvious thing, the obvious there, but there are very subtle changes on that could happen, as in if this piece of code there was in a function call or a mode that will use something else, and when you call it from there, that constraint could never be reached. Now, argument is, leave the code there, because if you cannot execute it, you cannot execute it. So it's okay. Now, depending on the industry, this is not allowed. You have to remove it, which means doing the change, document the change, review the change the documentation, repeat the tests. So that's a very painful process. So better avoid it in the first place. The other one is, well, we are not allowed to touch that code. I mean, I was visiting to a customer, there was something like this. It was obvious that the only way to do was to remove that piece of code. They said, you know what? We developed that code, and we got that code developed by a subcontractor. The contract says we shall not touch the code. If we touch the code, we have to open the contract and pay a big amount of pound notes to that person to remove that line of code, and we do it. That is a reason to justify why you shouldn't do it. So I find it entertaining sometimes where in other industries code is fluid. Agile development is code is easily modifiable because anyone can. In the safety critical industry, basically the last thing you want to touch is a single line of code, even a comma, even a comment. So, important here, both ISO 26262 and UN 7AB and C says that code should be removed. There's actually a paragraph that says that. In ISO 26262 which I is a bit more lenient, and then if you really insist that you may be able to do that, but you have to actually provide a rationale for that. Now, there's a difference between that code and deactivated code. Deactivated code is code that is not dead, but in the mode of operation, that could not happen. For example, could be diagnostics. So I may have my piece of stuff that runs on the aircraft, and there is one diagnostic node, that it should be there. So the code will not be executed on site if I cannot test it, but there is a different mode that it could be. Again, this is the kind of thing where providing justification to say, well, this is a diagnostics code, and therefore we should not use it, and therefore it can be removed. Or You redesign the code and take it out. Sometimes this is not possible because third-party code, you cannot touch it, or is inherited code that you don't want to touch it, because if you touch it, you don't know what else you're going to break. Defensive programming, another one. Coding guidelines. There shall be always a default statement or a switch statement. However, your variable A can only be 0, 1, 2, and 3. So if you don't have the last line, your style checker, your programming style checker will complain. And then you have to justify that. Or, if you follow that one, this can never be executed because, by construction, A can only be from 0 to 3. Defensive programming can be doing redundant checks. If the variable is wrong, outside the bounds, fix it. Not within the bounds. If the variable, and then later on says, if the variable out of bounds, I cannot do that, just checking now. So you could only do in between these two, something that really won't go wrong. But that's very, very difficult to test. Impossible combination of events. Again, in complex software, you may have modes of operation that preclude the execution. So, for example, the second statement, the second condition cannot be, cannot happen because a label may be already been set at this point. So again, this shows that code is too complicated, and possibly a peer review would say, oh, I don't like this, you may have to rewrite it, or justify it as part of the design. And then this, and the final one is compiling to use errors. Now, this is very seldom happens, but is something that is actually quite risky. We did a compiler verification project for a customer where we run a whole battery test and we look at the quality of the code. The code is correct, as in functionally correct, but it was not safely critically correct. Because the compiler is something that worked, but if you were writing up as an assembly yourself, put it like this, you wouldn't dare to do it. So there are some vulnerabilities of the underlying that makes more fragile to external influences. I can talk about it more later on. We have a case study that people can have access to. So I'm just going to skip that one to get the gist of what we got here. So we only have a mechanism that you can add justifications in the code to automatically produce as part of the analysis that my code has 100% code coverage because I tested 97% of it and I justified 3%. And the justifications are part of the environment. So therefore, you reduce the manual headache of, at the end of your test strategy, having to write a Word document, typically, where you say exactly why that piece of code cannot be tested. And on the next release, that document has to be edited again. And the next release, edited again. So we put a lot of effort into making it part of every tool, a justification workflow supported by reviews, and also that allows to migrate the justifications from one revision to the next one to say, after I justified on my holes because defensive programming, invalid modes, some conditions are a bit effort because of legacy code, all these still allow you to achieve 100% code coverage. And the colorization in our tool shows green means tested, red means not tested, and blue means justified. So for as long as there's no reds, we are fine. So summarizing, what do we do with less than 100% code coverage? You first understand why you don't have the missing code coverage. We have a list of 7 items. Please tell me something else I don't know. Next one is, usually we either remove the code, have to fix it, fix the requirements, or fix the code, justify why we won't execute it, or why it's impossible to test. Have I missed something? Can you tell something else that has happened in your life that couldn't be covered here? Yeah. So I have some facts and information outside that show our company, our tools, and how we operate. We're happy to explain what are the advantages of our tool. But by the way, it also has an integration with MATLAB Simulink. And we also do timing analysis, code coverage, worst case execution time that we mentioned before. So anything that you're ready to on target. Okay? Thank you very much for your time.
Yeah. We've got time for just 1 or 2 quick questions.
Yes.
So I'd just like to ask about dead code. So I have an extraordinary dislike to dead code, as in I'll jump up and down and kind of cry when I see it. And this comes about because of security. So when you compile code and it's running, so dead code can lead to a point where a memory pointer can jump and suddenly it's executing that dead code. Yet apparently it was impossible to do so. And what a lot of hackers do is they look for ways to manipulate the memory of the system to force it to execute things when it shouldn't. Dead code, for example. In my mind, security and safety critical systems must have an intrinsic relationship. You know, you want your network on your airplane to be secure, for example.
Yeah.
So I found it, could you explain why one of the things that you showed said that in a safety critical system, you don't need to remove dead code. It was one of the standards. I don't understand that.
So the 178 says you have to remove dead code, but you could make the argument that why you can leave it there if it's not possible. For example, automatically generated code. You don't want to go back to your automatic code generator that generates something, and then you have to do a lot of extra work to justify that it's safe to leave that code there. The 170 says you have to remove it. Maybe these slides didn't give the right message, but the default behavior is that you're not allowed to have dead code, full stop, for exactly the same reason. But if there is for some reason, then you have to justify it and do a lot of extra protection. Yeah. But I agree, that's the point.
One more.
I would like to know if we are using a third-party compiler, specialized compiler, to generate the object code, and that object code is not disclosed by the third party. In such scenario, how do we do the compiler validation, and how do we ensure that object code and the source code are equivalent?
Probably by paying a ridiculous amount of money to the compiler vendor to tell you that this is the case.
Okay.
That you, right.
Yes. What I want to understand is that, if we have got a specialized compiler which generates the code, which compiles and generates the executable code, and that executable code is not disclosed by the third party whom we have brought the compiler. In such scenario, how do we ensure that the object code and the source code that we have written are equivalent, in equivalency check? How do we ensure? Yes.
But you cannot see it.
Because there are third-party compilers which we are using in our project as well, who do not, third party does not disclose the object code. Compilers, yeah, compiled executable.
You are not allowed to disassemble the object code.
Yeah.
You have it, but you're not allowed to disassemble. We've seen that in a... No, they want to see want to see what is the object code the compiler generates. You are not allowed to.
Okay. Probably won't take too long to answer this question. I think we'll have to leave it there because we're running a little behind time. So on to our next talk.
Thank you.